Dear students, pre-processing logs can significantly influence the results of log data analysis. Next, we present some pre-processing steps that may be useful in conducting log data analysis. This slide illustrates the log processing pipeline used in our LogLead tool. First, logs are collected from various systems. Second, the log data is standardized into a common format. The raw logs are processed into a structured representation, typically a data frame. Key fields like timestamp, severity level, and message content are extracted and organized, making the data easier to work with. Third, enhancements are introduced to generate alternative data representations, such as character-level n-grams. Finally, anomalies are detected and scored. These scores highlight unusual patterns or deviations from normal behavior, pointing out potential issues that require attention. By following these steps, the pipeline enables the use of a unified approach for processing logs from multiple systems. The process begins by treating each log event as a single line in the log file. Each line represents an independent event, forming the foundation for subsequent parsing and analysis. Then, the log lines are sliced into different columns to make the data more structured. In the example shown, each part of the log line is clearly shown. For instance, the timestamp indicates when the event occurred. The thread ID identifies which thread generated the event. The log level gives the severity of the event. The component specifies the source of the log message. The log message contains the actual information or context of the event. Next, we might need organizing log data into meaningful sequences during the load and process stage. First, logs can have distinct phases corresponding to different parts of a process or system activity. These phases need to be identified and separated. For example, in continuous integration (CI) systems, different steps such as building, testing, and deployment generate unique logs that should be treated independently. Second, if multiple threads push to a single log file, separating logs by their source or purpose is critical. In the case HDFS log data, each block ID represents a distinct data transfer. In HDFS dataset, logs consist of 10 million lines, but grouping by block ID reveals roughly 500,000 unique sequences. Third, different parts of logs can reflect different tasks within the same file, such as initialization, fulfilling specific requests, like add to basket or checkout, or restarting services. Identifying and isolating these tasks allows targeted analysis of specific functionality or issues. This separation may be necessary as a foundation for accurate and efficient log analysis, but its relevance depends on the specific system being analyzed. Before logs can be analyzed effectively, it is very likely that we want to mask certain parts of the log messages. Masking helps focus the analysis on relevant content by concealing information that is not essential or even misleading for the model to process, such as timestamps or IP addresses. In our work, we encountered instances of incorrect log analysis because we forgot to mask timestamps. This oversight caused the clustering process to focus on the dates in the logs, rather than the actual events described in the logs, leading to inaccurate clustering results. Obviously, masking introduces a trade-off. While it can reduce the likelihood of false positives caused by irrelevant variability, it may also lead to missed anomalies or root causes if critical information is masked. Striking the right balance often requires experimenting with different masking strategies. The figure at the bottom of the slide demonstrates masking with 3 log lines presented in 2 formats. The first shows the raw version, and the second demonstrates how the logs appear after masking block IDs with open angle bracket BLK close angle bracket and IP addresses with open angle bracket IP close angle bracket. The next step involves choosing an appropriate log representation and deciding what specific information to extract. First, selecting the representation depends on the goals of your analysis. For example, you may choose to use message length, sequence duration, or character n-grams, e.g. 3 grams, as features for anomaly detection. Message length might highlight unusually short or long log entries that are outliers. Sequence duration could reveal processes taking longer than expected. Character-based n-grams capture recurring patterns or anomalies in the text structure. We can also enhance logs with what is known as log parsing or log clustering. It is worth noting that log parsing is a dedicated research field with numerous log parsers available. These tools aim to transform unstructured log messages into structured representations that are easier to analyze. Log parsing or log clustering works as follows. It separates the fixed parts, templates, of log messages from their variable parts, parameters. For example, in the log message, connection open to 192.168.0.1, the fixed part is connection open to, while the variable part is the IP address 192.168.0.1. This process turns a stream of raw log messages into structured events, where similar messages are grouped based on templates. The benefits of this approach are substantial. First, it simplifies the analysis by reducing the complexity of unstructured log data. Second, it enables advanced use cases such as predicting the next event, constructing state machines, or analyzing look-ahead pairs in sequences. However, there are potential drawbacks. Log parsing can be time-consuming and prone to mistakes, especially when the templates fail to capture all variations accurately. Such mistakes may reduce the accuracy of subsequent analysis. Additionally, there's a risk of losing critical parameter-level information if the variable parts are overly simplified or excluded. Determining whether log parsing is helpful for a specific log analysis task requires experimentation.